Welcome everybody to the third lecture of electrostatic field. In this lecture, we'll be discussing the behavior of electrostatic field in different media. So in electrical engineering, we divide material into three different categories, which are conductors, semiconductors, and dielectric. Conductor materials like copper, silver, gold, iron, and almost all the metals. Dielectric material like wood, rubber, Teflon, and the insulators that we see around wires in electrical work. And semiconductor material, which is somewhere in between, like silicon, which we use a lot in electronics. We will start by discussing the behavior of electrostatic field in conductor materials. So in conductors, let me bring the, in conductors, rho, which is a volumetric charge density, will equal 0. Electric field equals 0. So there is, like, assuming the conductor is perfect, there is no charge, like there is no net volumetric charge density inside the conductor, and there is no electric field inside the conductor. So if we introduce a charge close to a conductor, so if we have two media, we are bringing a charge next to a conductor, it will affect this conductor and induce like some charges on the surface of the conductor, and those charges will be distributed to cause the field to reach equilibrium. So equilibrium means that the charges are stationary. We are bringing a charge closer, like assume that the surface of your disk is a conductor, and you are bringing a charge closer to the disk or closer to the surface of the disk. And then you make this charge stable, stationary. This charge will affect the conductor such that it will induce or attract or repel depending on the charge polarity, as we're going to see shortly. And all of this will happen very, very, very fast, and you will reach an equilibrium. At equilibrium, all the charges are stationary. Nothing is moving. I'm not talking about the charges around the atoms or like around the nucleus in the atom, but I'm talking about free charges on the conductor will be stationary. The conductor will be equipotential. All the points on the conductor, on the surface inside the conductor, will have the same potential. The electric field inside the conductor will equal 0. The electric field outside the conductor will be perpendicular to the surface. And we're gonna discuss shortly why is this. At the interface, like assuming that, again, the same example, the surface of our disk is a conductor, and we are bringing a charge on air close to the surface. The interface between the two media, first media is dielectric, which is air, and the conductor, which is the surface of your disk, and the interface between them is called the boundary between the two media. So this is the separation between the two media, is called the boundary. At the boundary between the air and conductor, there is some rules which we call boundary conditions. The boundary condition is that E tangential equals 0, and the electric field only at the surface does have a normal component. This normal component equal rho s divided by epsilon naught, which is the conductor, the dielectric permittivity. So we can prove the first one, the first boundary condition, by applying electrical potential conservative property. We know that, and we discussed this before, at the surface of equipotential or a contour of equipotential, the electric field must be perpendicular. And we're going to repeat this again. We know that if we choose any arbitrary points, B1 and B2, on the surface or on the boundary between air and the conductor, and we calculate the electric potential difference between point 2 and point 1. V2 minus V1 will equal this expression. Because B2 and B1 are arbitrarily chosen, DL will be whatever direction, but it will be always on the surface because the 2 points are on the surface. Okay, we know that the conductor is equipotential, so V2 equal V1, and this integration must equal 0. In order for this integration to equal 0 all the time, for any point B1 on the surface and any point on the surface B2, we know that DL must be like tangential to the surface. Then the only mathematical solution for this is for E to be normal to DL at all the points. So E must be normal to the surface. So any surface equipotential, the electric field is normal to it, and the conductor does have like an equipotential surface all the time, so the electric field tangential component to the surface always equals 0, which is the first boundary condition. If the tangential component is 0, so all the field will be normal, so we have E normal equal E. Okay, how to like prove this? Second boundary condition, which is E normal equal rho S divided by epsilon naught. Rho S is the surface charge density. So to prove the second boundary condition, we need to choose like a Gaussian surface that is having an axis normal to the surface. So we can choose like a cylinder or a box, but its axis is normal to the conductor surface, and its height is infinitesimally small. One base will be inside the conductor, the other base will be immediately above the boundary between the conductor and air. So it is in air directly above the boundary. The other base is directly below the boundary inside the conductor. And then we apply Gauss's law. Gauss's law, left hand side is E dot ds. It will be divided into 3 components: lower base, upper base, and the side. The flux on the side will equal 0. You should know the answer. Why is this? We did this before. Think about it. And you should reach the conclusion that because the electric field is normal to the surface, so E is normal to the surface, while ds on the side is parallel to the surface. So E dot ds will equal 0 because E and ds are perpendicular to one another. The flux on the lower base also equals 0. You need to think about it. Why? We just said that the electric field inside the conductor equal 0. Why is that? Because any 2 points inside the conductor does have the same potential, so there couldn't be any field between them. So there is no electric field inside the conductor because all the points inside the conductor are equipotential. So the flux, or E dot ds, on the bottom equals 0. On the top we have E normal to the surface, of course, because the upper surface is very close to the boundary. ds is also normal, so E dot ds will equal the normal component of electric field multiplied by ds. The total charge enclosed by this box equal rho surface multiplied by ds divided by epsilon naught. So just equating the 2 sides, and we get En equal rho surface epsilon naught. So the electric field is normal to the conductor's surface, and its value equal to the surface charge density divided by epsilon naught. No tangential component on the surface of the conductor, no electric field, neither volumetric charge density inside the conductor. Okay, so let us use this information, or let us solve this example. The example is given the following setup. We have a positive charge Q at the center of a spherical conducting shell. So we have like a spherical, like a hollow sphere, or a hollow sphere with inner radius R input, R inner, and outer radius R out. And in the center of this conducting sphere, there is a point charge that is positive at the center. And we are requested to determine E and V, the electric field and electric potential, as a function of the radial distance R. So we need to think about this problem. The problem is like spherical, so the first thing comes to mind is that we're going to use a spherical coordinate system. There is symmetry because of the setup, so we shouldn't expect any dependency on theta or phi. Everything will be just depending on R. And we also need to consider three different regions. Region 1 outside the sphere, region 2 inside the body of the sphere, or like inside the conductor shell, region 3 which is inside the conducting sphere. And we need to solve. This problem does have symmetry, so Gauss's law would be a very suitable for solving this problem. And as we see, we have three regions, so we need to apply Gauss's law 3 times. We start by the outer region, region number 1, and we're going to apply Gauss's law, E dot ds. Because of symmetry, the electric field, we know it will be normal to the surface because it's radial, and it is uniform because there is no dependency on theta nor on phi. So the electric field on Gauss's surface, any spherical surface outside of the spherical conducting shell, so the electric field in region 1 multiplied by the area equals the total charge enclosed by the Gauss's surface. So what is the total charge? The total charge is positive charge Q. We're gonna talk later about this negative and positive sign. So the field in region number 1 equal Q over 4 pi epsilon naught R square. To find the electric potential, so the electric potential is the potential of this specific point minus the potential at infinity, which is 0. So it's E dot dr with a negative sign from infinity to R, which will equal Q over 4 by epsilon naught R. So you can notice here the electric field in the outer region is similar to the case of point charge in free space, as if this conducting spherical shell doesn't have any effect outside of like region number 2. Same thing for electric potential. The electric potential at a point in region number 1 is very similar, is exactly the same as the electric potential because of a point charge at the origin. So in region number 1, the conducting spherical shell doesn't have an effect. If we go for region number 2, so we need to find electric field inside the conductor. This is like this dark gray is a conducting material. We need to find the electric field and the electric potential. We know that inside the conductor, electric field equals 0. We know also for the conductor, the electric potential at any points inside or on the surface does have the same value because conducting material is equipotential. So in region number 2, electric field equals 0. The potential of all the points, electric potential of all the points is the same. So what is the value of this constant, this equipotential equal what value? So we can find the electric potential on this outer surface, which is just like applying R out here. This will be the potential on the surface. So all the points on the surface does have Q over 4 pi epsilon naught R outer. All the points inside also does have the same value because it's an equipotential surface. So the electric field in region number 2, the electric potential in region number 2 equal Q over 4 pi epsilon naught R naught. Okay, if we go for region number 3, which is inside the conducting shell, and applies Gauss's law, we'll find that electric field in region number 3 equal Q over 4 pi epsilon naught R square. To find the potential in region number 3, we need to find the electric potential difference between this point. So this point is known, like the potential at this point is known. The potential at this point equal Q over 4 pi epsilon naught R outer, because it is on the surface of the conductor. And we can find the potential at any arbitrary point inside by the difference between the known point and the point of interest, which equal let me write this in a better way. Okay, so in region number 3 we have the electric field with this expression. In order to find the electric potential in region number 3, we can apply this expression V3 minus V at Ri. So Vi is the potential at the radius Ri. Why we are choosing Ri? Because it is a known potential at the boundary between region 2 and region 3. What is the expression of Vi? It's the expression of V2. All the points in and on the conductor's surface, in the conductor and on its surface does have the same potential of Q over 4 pi epsilon naught R naught. So this is Vi is known. So the potential difference between V3 and this known point equals the integration of E dot dl, because we are moving on radial here, Ri to R. So the expression in region 3 does have this expression or this value. So V3 will equal, this will go to the other side as a positive, Q over 4 pi epsilon naught R naught, plus the integration of this with respect to R, which is negative, will cancel this negative sign, and it will equal Q over 4 pi epsilon R from Ri to R, just substituting and rearrange the terms. Okay, so one extra point here, let me remove it. Okay, so this is the electric potential in region number 3. We can draw the electric field as a value. The electric field will be from outside, like going from outside to R, from outside 0 at infinity. It's increasing as we get closer till we reach R out, then it's 0 inside the conductor, then it has like a growing value inside region number 3. The electric potential is 0 at infinity. It will reach certain value. It will remain constant inside the conductor, then it will increase as we're getting closer to the point charge. Okay, so here coming to the point of positive and negative charge, we can recall the boundary condition of the electric field on the surface of a conductor, that electric field is normal and equal rho surface over epsilon naught. So if this is a positive charge, so the electric field is going in that direction. Okay, and we recall that En, let me bring it. Okay. So we have this boundary conditions that En equal rho S. N here is out of the surface. The electric field is going inside the surface, so the surface charge will be negative. So that's why we have negative surface charge on the internal side of the conducting shell. And because of symmetry, these charges will be uniformly distributed on the inner surface. What is the value? We can get the value from the electric field, but also you will find that from physics, the total electric charge on the inner surface equal minus Q, because this positive charge will attract negative charges on the inner surface equal to its value, and they are uniformly distributed because of the symmetry. Because we attracted negative charges to the inner surface, will repel positive charge to the outer surface. The positive charges on the outer surface equal the same negative charge, which equal to plus Q, and they are uniformly distributed on the outer surface because of symmetry. Also, if you continue this way, we know that the electric field on the outer surface is going out, so it is in the direction of En out of the surface. That's also like an indication that on the outer surface the charge is positive, because En is in the same direction of An, the normal to the surface out of the surface. So that's why, or those are like a number of explanations for the negative charge on the inner surface and the positive charge on the outer surface. Now coming to the second category of material that we're going to analyze, which is the dielectric material. The dielectric material is characterized by having positive charge in the nucleus and negative charge in the electrons orbiting around them, and they are very tightly coupled. There is a very strong bond between the positive charge on the nucleus and the negative charge on the electron, and they are forming some sort of a dipole, and this is where we recall the electric dipole. Two positive and negative charge, two identical charge of opposite polarity, are coupled to each other at a very small distance, and those two charges are the electron charge, which is negative, and a corresponding positive charge of positron inside the nucleus. So when exposing a dielectric material to electric field, there is no way to induce charges because there is no free charges. So the thing that happens for dielectric material is that the electric field will cause the electric dipoles that we just described to slightly orient, or like to start to orient itself along the direction of the electric field. So the positive charge will try to align along or move in the direction of the electric field. The negative charge will move in the opposite direction. And this process of like trying or like affecting the internal structure of the material is called polarizations. So the electric field is causing the charge or like trying to move the charges in a certain way, and the internal structure also is opposing or is imposing different force. So there is a partial polarization that is varying from one material to the other. So some material does have polar molecules, and this is based on the internal structure of the material. If there is no electric field applied from outside, those polarization molecules or polarized molecules will be, they are very large numbers. Their number is equal to the number of electrons in the material, and they are of course randomly distributed, so the net effect would equal 0. Some other material, they don't have this kind of molecules. Some dielectric materials, they are not that famous, does have their dipoles arranged in a way that there is an electric field inside them, and they are arranged in a aligned way so that they produce electric field even without having any external source. So the net charge is 0, but aligned in a way that it has some permanent electric field, and this is similar to the permanent magnet. It's called electrets. Okay, so how would we analyze the electric field inside a dielectric material? So if we have like a very large, or like if we have a certain number of dipoles in a volume, how would we like model their effect? We model their effect using the polarization vectors that we introduced 2 lectures ago. And the polarization vector is a vector, so we have like a vectorial summation of all the polarization vector existing in a certain volume. And if these are very large number and continuous, we like convert this summation into vectorial integration. We had proven that the dipole moment produced by certain like magnetic dipole to have this expression. So if we have a certain volume and we would like to calculate its electric potential, the electric potential caused by those dipoles, we'll have just integrating this dV over the volume, and this would be the total potential due to the material polarization. With some mathematical derivation, we can prove that the volumetric charge density of electric dipoles is related to the electric the polarization vector using this expression here. Of course, the volumetric dipole density is a scalar quantity. The polarization vector is a vector. The gradient of a vector is a scalar. Okay, so back to Gauss's law. We are trying here to characterize or model the effect of dielectric material. We have E dot ds over any closed surface to equal the total charge enclosed inside this surface. Now we have two kinds of charges. We have the free charges and we have the polarization charges. So if we take this into the divergence theorem, or if we apply divergence theorem, divergence of electric field will equal the rho free over epsilon naught plus rho p over epsilon naught. We just proved here rho p equal minus gradient of polarization vector. So here, just like, let us review the terms that we have here. Rho t is the total volumetric charge, which is composed of two kinds, the free charge and the polarization charge. Rearranging this equation, we can bring the gradient to the other side. It would be the gradient of E plus the gradient of P, which is, and we multiply by epsilon naught. So it would be the gradient of epsilon naught E plus the polarization vector, and this will equal the free volumetric charge. We took this expression and we call it the electric flux density. So the divergence of the electric flux density, or also it's called electric displacement vector, equal the volumetric free charge density. And this is like a second form of Gauss's law. So we can rewrite Gauss's law in general, like in free space, in conductor, in dielectric, in any material as such. The divergence of D equal rho F, or D dot ds over any closed surface equal the total free charge enclosed inside this surface. Let me adjust this. So D dot ds over any closed surface equals the total free charge enclosed by this closed surface. So now, when the dielectric material is linear and isotropic, isotropic means that its behavior is independent of the direction of the electric field. If the material behaves differently for different directions of electric field, it's called non-isotropic material. But if the direction of electric field doesn't affect the behavior of the material, it's called isotropic material. If the material is linear and isotropic, the polarization vector is linearly proportional to the applied electric field. And the constant of proportionality is called susceptibility. Susceptibility, xi, is introduced here. So back to the definition of the displacement vector, of the electric displacement vectors. It's equal to epsilon naught E plus P. If we just substitute B here, we'll find that the displacement vector equal epsilon naught multiplied by 1 plus xi E. We call 1 plus xi as epsilon r, and it is called the relative permittivity. So we are introducing here a very important parameter in electrostatic and in electromagnetic in general, which is the relative permittivity, which equal 1 plus susceptibility. One important parameter of the dielectric material is called the dielectric strength. So it is the maximum electric field intensity a dielectric material can withstand without breaking down. What is the idea of breaking down here? That, as we show here, that the dipoles will try to align themselves along the direction of the applied electric field. So the stronger the electric field, the more separation between the positive charge and negative charge gonna be. So the electric field is trying to separate the electrons and positron apart from one another, and increasing the strength of the electric field will cause this separation to increase till we reach a point that the positive charge and negative charge are completely separated. And in this case, we are having like a what we call like a breakdown of the dielectric material. Like you can see this, the dielectric material, for example, like when you have an insulator, if you put like very high potential, the insulator will burn. So this is, we damage the insulator internal structure and we caused a breakdown. One very famous phenomena of breakdown is the lightning. When we have like a storm, like we have like a discharge of the charges from the clouds to earth. So the air is a dielectric material. This dielectric material does have certain like strengths. It can be an insulator for like certain value. With the accumulation of very large amount of charges in the clouds and with the presence of like moisture in air, the dielectric material, which is air with some vapor, will become less and less weaker dielectric, weaker insulator. At a certain time when the accumulated charge is very large, there will be a breakdown. The air will be ionized, the positive charge in one direction, the negative charge on the other direction, and the cloud would discharge to the earth. And this is a breakdown for the insulator, which in this case is the air. So this is a breakdown. Sometimes you are using this breakdown property for our benefit, like inside the piston of the motor. So we have air with some gas moisture, and then we increase, like we apply like a high potential on the bijou, on the sparking plugs, and the separation between the two conductors is very small. And then because of this high potential and the vapor of gas or benzene into the piston, there will be a discharge. So it will sort of like explode because it released like a spark, and this will explode the gas. We use this explosion to move the piston and have like the car or the motor moving. Okay, don't forget to solve those examples from the book to like understand things better. Okay, we talked before about the boundary condition of the electric field on the interface between air and conductor. So now we're going to talk about the boundary condition of the interface between two media, two dielectrics. In order to like develop those boundary conditions, we would use those like two geometries. The first one, we would use like a closed surface, like a very small height of a cylinder with the axis normal to the boundary, and just a closed contour like a rectangular. The rectangular is having again very small width and like also a small height. It's very tiny, infinitesimal square. The surface, this edge is parallel to the surface, the other two edges is normal to the surface, and we would apply the two major postulates or general rules that we have for electric field. Number one is Gauss's law. Number two is the conservative property of the electric potential. We need just to pay attention here to the definition of the normal vector to the surface. A1 normal is normal to medium 1, and it's going out of medium 1. So it goes from out of medium 1 into medium 2. A2n is going out of medium 2, normal to the surface, so it's going inside or like to the direction of medium 1. Applying the conservative law of E dot of electric potential would have E dot dl over any closed contour equals 0. This is our closed contour, and because the potential between the point and itself equals 0, this normal edges to the surface are very small, so we just have the tangential component, and from this we can prove that E dot tangential component is continuous. E tangential 1 equal E tangential 2. The second one is applying the Gauss's law, D dot ds here, because the height is very small, we can neglect the flux out of the side. We have now the flux from the top surface and the flux from the bottom surface. Remember that the top surface is going in the direction of A to N. The bottom surface is going in the direction of A 1N. So D1 dot A2N plus D2 dot A1N. A1N and A2N, of course, are the negative of one another. So the difference between D1 and D2 equal the surface charge density. It depends which one is the reference we can find. So if D1 is greater, D1 is the normal component out, is larger than the normal component in, it would give us like a positive charge on the outer surface. So the difference between the normal component of displacement vector equals the raw surface charge density. Okay, so let us apply the boundary conditions on this example here. We have a sheet of dielectric material. The dielectric constant is given. It is introduced perpendicular in a uniform electric field. So we have a uniform electric field here, and we need to find the electric field inside the dielectric material. So in these cases, we need to find the boundary conditions and equate the boundary conditions to find the electric field. So here, this is a dielectric material, so no surface charge is introduced or mentioned. So unless we insert surface charge on the dielectric, it will not induce electric charge by itself. So here we have the electric charge equal 0. So we have two boundary conditions. One is E tangential, the other one is D normal. Because here the electric field is just normal, we must use only the D normal. We have DI, which is inside the dielectric material. DI, it will equal D naught because there is no surface charge. Once we know DI, we can calculate EI. EI equal 1 over epsilon DI. So we have the solution for the electric field. We need to find DI. We find it from the normal boundary condition under the assumption that there is no surface charge. From D, we can find E by just dividing by epsilon r. To find B, we need to write the expression for D. Remember, where we write the definition of the displacement vector, it's equal epsilon naught E plus B. So B will equal E minus epsilon naught E. So electric field equal 1 over epsilon naught epsilon RD. So B equal D minus epsilon naught E, which equal 1 minus 1 over epsilon r multiplied by epsilon naught E naught, so we can find the value of the polarization vector. Also here, I can ask you about the electric field in the outside, and you're going to apply something similar. So in the outside, di must equal on the other interface. So here we have two interfaces, interface 1 and interface 2. di normal equal d out normal, because there is no surface charge here. From d out we can find E naught, and we can find polarization. If this is a free space, we'll find that d naught equal to d naught, E naught equal to E naught, P naught equal what? Equal 0, because it's free space, no polarization. Okay, another problem that we would like to solve. We have like two dielectric material. The permittivity is epsilon 1 for medium 1, epsilon 2 for medium 2. There is like charge-free boundary, so rho surface equals 0. The electric field in medium 1 is given at a point on the interface. The magnitude is E1, the angle is alpha 1 with respect to the normal. We would like to find the magnitude E2 and the angle alpha 2 with respect to the normal at point 2, which is directly below point 1. Point 1 is in medium 1, point 2 is in medium 2. They are across the side from the boundary. So we solve this problem by writing down the boundary conditions. We have one boundary condition regarding the tangential component of the electric field, and one boundary condition regarding the normal component of the displacement field. So we need to write them. This is sort of like a direct application for the decomposition. We have the electric field in that direction, so it has a normal component and it has a tangential component. Same thing for E2. So we're just writing the boundary conditions. The tangential component of electric field 2 equals the tangential component of electric field 1. Tangential component equal E1 sine alpha 1. Tangential component equal E2 sine alpha 2. So this is the tangential component of E2, and this is the tangential component of E1. They are equal to one another. The normal component of displacement vector 2 equal epsilon 2 E2 cosine alpha 2. The displacement field normal component in medium 1 is epsilon 1 E1 cosine alpha 1. So we have those two equations. In order to like find the value, we can just divide the two equations. We'll have we'll have tan alpha 2 over tan alpha 1 equal epsilon 2 over epsilon 1. Epsilon 1 is given, epsilon 2 is given, alpha 1 is given, so the only unknown here is alpha 2. From this equation we can find alpha 2. Substituting alpha 2 here, alpha 1 is known, E1 is known, alpha 2 now is known, so we can find E2, and we solved the problem, which is we found the magnitude of electric field in medium 2 and the angle between the electric field and the normal to the interface in medium 2. So in this equation, in this lecture, we learned the behavior of conductors in electrostatic field, the behavior of dielectric material in electrostatic field, and we learned about the boundary conditions, the tangential boundary condition and the normal boundary condition. This boundary condition is very useful and used very frequently in electromagnetics in general to solve problems. So I hope that you study it carefully and understand its details. Thanks for watching the video, and meet you in the discussion session.